Let's look at some examples of what you can do with GANs. And these are not state-of-the-art results from GANs. This is a research area which is evolving so fast as we speak. There are thousands of papers every year, so it's essentially impossible to stay on top of the state-of-the-art with a lecture unless you redo the lecture all the time. And therefore, I just want to show you some of the ideas. So what can you do with a GAN? What tricks can you play with this sort of generative neural networks? So one of the tricks that we have seen earlier is that you can use latent spaces of generative networks in order to do interpolation between the objects of interest, for example, images. And interpolation in a meaningful sense, in a sense of finding pathways that go through the manifold of the objects defined by your probability distribution in your database. And so you can go further than that. So interpolation, linear interpolation means you're doing some linear operation in that space. But if you can do this, if you can do linear interpolation, maybe you can also do other arithmetics. So other linear operations, such as adding and subtracting things. And so here's a fun example of that. So you have samples of men with glasses. So these are generated samples, so they look a little bit weird. But now state-of-the-art GANs generate really impressive and amazing pictures of humans that you cannot distinguish from actual humans. And but so this is a quite old this is quite an old example. So anyway, these are men with glasses, and now we take images of men without glasses, and we take images of women without glasses, and we do the following operation. We take a sample of men with glasses, subtract a man without glasses, and add a woman without glasses. We do this operation in latent space. Yeah. So we basically take we take three vectors in C space, so the input space for the generator, and these two here correspond to men with glasses and without glasses if we go through the generator. And this one corresponds to a woman without glasses. We go through the generator. And then we do this arithmetic operation. So we get the resulting Z vector, put it through the generator, and then we get women with glasses. Yeah, so that's a fun example. Of course, this sort of operation is completely meaningless in pixel space. If you do this operation in pixel space, you just get random noise. Not completely random, but you get something which looks very much like garbage. Whereas you get meaningful results if you do this operation in latent space. As in conditional variational autoencoders, you can also train conditional GANs by adding a condition, for example, a class encoded with a one-hot encoding into the generator and the discriminator, and then you can train the GAN using this condition of the labels that you have in your data set, or the labels that you want to generate, and then you can use this condition later in the generator in order to sample from specific classes. So here are examples of rather old by now convolutional GAN. So where we have convolutional neural networks for the decoder and also for the generator and the discriminator. And these are samples of birds, ants, monasteries. And you can see they kind of look like ants, but they're not really correct or complete. They have missing global information, whereas volcanoes are apparently much easier to generate, and they look pretty impressive. Here is a newer example, which is essentially doing inpainting on face data. So inpainting means we erase part of an image, or we have a missing part of the image, for example, because it's covered by something. And then we ask the question, what is under this missing part? Can we complete this missing part? And this is a somewhat more complicated network structure. It combines the idea of autoencoders and GANs, and it has global and local discriminators, because we want something that looks globally right as a face, but also something that looks locally right, so that generates meaningful information in the piece that we complete. And then we train this essentially as a GAN. And here you see that you can very nicely complete missing parts of faces, as you see here. So in this first set of images, you get very nice completion. But of course, you also see that you cannot see what you don't see. So for example, in this image here, the lady with the glasses, if we just erase the glasses, well, we don't know that there were glasses here before erasing it. So the generator might just add a pair of eyes without knowing how the eyes of the woman actually look like. And here you see a similar example. Here you see an interesting example from the Schölkopf group. These are GANs that are conditioned on quite complex objects. So instead of just conditioning them on a class, we condition them on a sketch drawing. So here, for example, we have images of boots, and we condition them on the sketch of just the edges of the boot, so like a cartoon sketch, if you like. And then we learn to generate the boot image conditioned on the sketch. And this is, of course, very nice for cartoon drawers. Basically, you draw a cartoon, or designers, fashion designers, you draw a cartoon, and then you get something that looks like a photo based on your cartoon. Or you can do things like start with maps, so the map view from Google Maps, for example, and train with combinations of maps and the satellite or aerial photo. And then you learn to generate the aerial photo from the map, or vice versa. These are other outputs of this conditional GAN. So a very nice illustration how we can go from sketches to photorealistic images of these objects, and this is very nice for photo designer, for fashion designers. Finally, I want to end with a very important development in the GAN world, which started with this paper, Progressive Growing of GANs. And the idea is the idea is the following: for GANs, or generally for generative neural networks, before this paper appeared, before 2018, it was relatively feasible to generate small images, so images with not a too high resolution, not too many pixels. But it was very difficult or infeasible to generate images that are like 1024 by 1024. And this paper made an important step forward in that direction by viewing this problem as a multi-scale problem. Remember, convolutional neural networks with pooling are essentially using a multi-scale idea for classification. Yeah, they have these convolution operations, and then you pool down to a lower dimensional representation of your feature maps, and then you convolve again, pool, etc. So here is a multi-scale idea for GANs. We take our images, which are high-res images for training. So let's say they're images from a 1024 by 1024 data set, like this Celeb A data set here of VIPs or celebrities. And now we scale them down to 4 by 4 images. So basically we just divide them into 4x4 supercoarse pixels, and we sum up, or we average over these segments, and then we get these super blurry images where you essentially can't see the face anymore. But now we have small, low-dimensional problem, and we can easily train a 4x4 GAN to generate samples from these 4x4 images. Now we fix those parameters pertaining to the generator and discriminator of the 4x4 image, and now we condition on that generator and discriminator for 8x8 images. Train those parameters with a GAN and continue. In the end, everything is trained, so all the parameters are relaxed and trained. But in that way, we have essentially simplified a big part of our training problem. We have for every additional layer which trains the next higher resolution of these images, we have already positioned the parameters of the other parts of the GAN in a regime where it's much easier to train this next set of parameters. And with this trick, it becomes possible to sample these very high resolution images. And these are actually samples from this progressively grown GAN. So these are really completely made up generated samples of the generator that has been trained with the CelebA data set, so using celebrity images that are of similar size and quality, but these people do not actually exist. They just look important, so they are a good representation of celebrities, but they do not actually exist. They're completely made up, and they look really, really impressive. Now, obviously, with faces, the situation is a little bit easier than with other more complicated objects, because these faces have obviously many aspects in common. They usually have two eyes, one nose, one mouth, hair, etc. And everything is more or less in the same place because these faces are aligned, they look to the camera, etc. So you could argue they are not so many variables that you need to be able to vary. The underlying manifold representing faces is perhaps not that high dimensional. And indeed, you see that when you try to use the same technique to generate, let's say, airplanes, and some of these airplanes look pretty good, others clearly won't fly because they have like missing parts or are disintegrating. So obviously these GANs are a great image processing and image generation framework, but they cannot do physics, or they cannot really understand gravity or what makes an airplane fly. It's so putting the local parts of an image into the correct global relation requires a quite deep understanding and requires either looking at many more examples and somehow learning by heart what that means, or having a somehow more structured and representation of what it means to build a correct airplane, or how to put things in a bedroom in a way that makes sense. Or how a bird looks like, or a bicycle that will actually run, etc. So with this, I'm finished with the second part of the directed generative network lecture. We have seen aspects of variational autoencoders that include classification in it, such as conditional variational autoencoders and classification variational autoencoders that you can use to do semi-supervised learning using datasets where you have many unlabeled and some labeled images. And then in the second part, we have looked at GANs, generative adversarial networks. Those are great state-of-the-art methods with which you can generate very impressive high-resolution images, and there are many variants of them where you can, for example, take an image from one style, transform it to another style. You can generate conditioned on some class. You can train networks which take a sketch and produce a photorealistic output with that sketch. As we speak, the state of the art in GANs is style GAN. That's a follow-up paper by NVIDIA on the progressive growing of GANs, which generates 4096 by 4096 sized, so super resolution images of faces in a very impressive way. But there is continuous progress in this area, and basically the state of the art here changes very rapidly, and there is a lot more to come. And with that, I'm finished with this lecture. Thank you for your attention, and see you in the next.